Welcome to the course on FPGA based signal processing systems. The digital modeling of the circuits, or the modeling of digital circuits we had seen, and in continuation to that, test benches, how to write those test benches, the test bench simulation and the synthesis of this Verilog modules will be discussed in this lecture. So, modeling of digital circuits, the structural model and the data flow model, also the behavioral model. We can see a few examples like the logic gates, built-in logic gates in Verilog, also the half adder program, full adder program, 2-to-1 multiplexer, instantiation of modules, built-in gates, as well as how the instantiation of the module inside a module can be done. There are two types of instantiation, that is with the port names we have discussed. In that, apart from the discussions, a few more examples, and we will be digging into further about the structural data flow and the behavioral model with more examples, and the syntax of Verilog for other cases also will be discussed. So, here this HDL design flow, if you just recall that, go back and see that this front end part we are doing that in the block diagrams of the model has been either done it in the paper or in the software, this block diagrams, and then the coding related to the Verilog code we have done, and the compilation part is a process which is done. Then the simulation or the verification, functional verification, without considering any timing parameters of the design. Also, what is this simulation part also will be discussing. So, the design flow, the design tools, the tools used for the HDL design has this two distinguished paths, that is 1 and 2, and anyway these two are cascaded with one after the other. The first part of the front end, and then the second part is the back end. So, the front end part we are doing, and will be whatever we have done so far. We would like to give more detail about the test bench, what is simulation and what is synthesis, and then more on synthesis will be discussed when we do the real time implementation of these Verilog modules, the design in the FPGAs. So, coming to the syntax of Verilog initial block, this is important to know because initial block is often used in the test bench. So, the initial block in the previous examples also you must have seen that the test bench what we had written had the initial blocks. So, the initial block syntax is the initial and then procedural statement. If there is only one statement that contains one initial, which is a keyword, and the procedural statement. Then comes the second format, or if you have multiple procedural statement. So, the procedural statement 1, and then it continues the procedural statements, and that would be within the begin end block. So, we have to accommodate these procedural statements, multiple statements within the begin end block, as we have also seen in the always block. So, in the always initial or the behavioral descriptions used for the basic behavioral description, and initial will be executed only once, that we are going to see in this. So, it's often used in the test bench. So, we like to give the syntax of this. So, it can be either having only one procedural statement, or it can have multiple procedural statements. Anyway, initial block doesn't have any inputs or sensitivity list. So, coming to this test bench. So, the test bench is used to do, it's again the Verilog program.v file, in this case in the Verilog module as we did in the previous examples also. It's a good program which specifies its behavior, and it is used to test the unit under test. That means the unit under test is not a device here, it's a Verilog module, that's a design, the digital circuit, that is a description in HDL is tested using the test bench with various inputs, and outputs are observed in that. So, it specifies sequence of inputs that is to be applied to the HDL design, that is a Verilog module. Also, it observes these inputs are it observes the outputs. Also, these inputs what we specify for the module is applied by the simulator to the module. So, this module it's very important, as any other module doesn't have any inputs. So module N module will have the module name, and there is no input and outputs. So they are specified in the test bench. Instead of that, the variables will be declared, input outputs, what we are going to use, what the inputs are going to be. That is, those inputs are from the, for the Verilog inputs, Verilog module inputs, and then the design inputs especially, and the outputs of the design will be considered for the declaration. So there is no inputs and outputs is explicitly said in the test bench. So it starts with the declaration of local signals. These local signals are the if you just recall the test bench we had done, so we have the port name and the local signals are specified. These local signals are here the inputs and outputs of the module which we are going to discuss, as how it is mapped and what is the type of signal, or how it is named in the test bench. So it starts with the declaration of the local signals, and these are the inputs and outputs which are used to apply the stimulus or the stimuli to the various combination of inputs applied to the module, and the outputs are observed from the unit under test. So it's not a device that the unit under test is used. It's a description of the design is tested over here for its functional correctness. And the initial block is often used in this. It is in the test bench, which is executed only once. So at the beginning, that when we say only once, it is at the beginning of the simulation, that is starting. So simulation time 0, that is t equal to 0. If you consider that starting time is the 0, then t equal to 0, that is it is executed. So the initial block is executed only once, and that time t equal to 0. So this also uses the delay statements. The test bench uses delay statements. You have seen in the examples that hash. So where hash symbols, hash is used for the delay specification. Hash 100 time unit, what should be the test conditions or the input conditions should be given to the module. So this specifies the delay statements. The test bench uses delay statements as well, and it uses for loop to generate all combinations of inputs. It is not only for loop, all test combinations. For suppose you have the 3 inputs and 1 output, then it needs to be the 8 combinations of inputs to be generated. So for that, for loop can be used. Since for loop is not introduced so far, that we have just explicitly mentioned what is the 8 combination of inputs in the examples what we considered for A, B, C and the full adder example, also 1-bit full adder. The for loop can be easily used for generating those test combinations of the design. And there are multiple ways also. It is not only the for loop helps in a test bench for generating the combination of inputs. It also where we can use the case statements. Even that for loop and case statements are one of the ways to generate the inputs. So case statement is also part of the, we can use it for combination of inputs generation. If this test bench also calls $display and $time, $monitor, all this task to print the results. So $time prints the time, the simulation time, and $monitor gives the what are the signals have been observed during the simulation. So that can be printed, and task, this is one task, and display, $display would also displays the signals what we want to, or this if you want to pop up any error message, also can be displayed over the $display using this $display task. So it uses all of this. So declarations of the local signals and for loops, initial block, for not only for loops, the case statements can be used for in the test benches. Now the time dimension. So the time dimension of the Verilog test bench. So how this time is handled in the test bench. Okay. So it has good facilities for modeling the time. Okay. So as I mentioned in the previous slides, it is time delay using the hash sign, and this is used with a real number. So the hash 100 or a hash 50, so can be used in the delay specifier, that is 1 facility which handles the timing. So suppose you give the input at a #100 and then another combination of input into the #20, or you want to generate a clock with a time period of something, we can use the delay also for generating the clock. Even we'll be looking at those codes in the when we deal with this sequential circuits. So this number is the units delay in units of the time scale. So what is this time scale mentioned or meaning in the test bench? So when we say the time scale, there is a default syntax, or the default time scale is 1 picosecond, but this can be changed, that the time scale can be changed in the test bench with the compiler directive, using the compiler directive. The compiler directive is this time scale. So it has the grave ascent. It starts with that grave ascent, and the time scale is the keyword, and it mentions the time unit in the test bench and the time precision, or what is the precision in which it is being handled. So the time unit here, this statement doesn't end with semicolon, that should be observed here. It starts with the grave ascent because it's a compiler directive. This is one of the compiler directives used in the Verilog for processes. And the time scale 1 nanosecond / 1 picosecond. So it's a time unit used, 1 nanoseconds, and the time precision is 1 picoseconds. So this is how the time mention is specified in the test bench. This is the unit which is used in nanoseconds, and precision is the granularity in which the simulator runs. Okay, so that's the time precision. So time unit, it can be, it need not be, it is nanoseconds here. It can be picoseconds or nanoseconds. And granularity, the time precision for the simulator operation is, it can go up to 1 femtoseconds as well, but the board should support for this. The FPGAs should support for the thing. It can be, ideally it can be done up to, the time precision can be of 1 femtoseconds for. And the waveform viewer. So the time dimension, the grave ascent time scale, time unit, and time precision, which we could also see in the waveform editor or the waveform viewer. So the waveform viewer, which displays the signal behavior here. So the here over simulation time. So the how much time we are running the simulation can be viewed over the waveform viewer or waveform editor. So this displays, so for example, in the case of AND gate or OR gate, the logic gates, we have used 2 inputs and 1 output, and then this 2 inputs A and B, output Y, inputs A and B, or how this is changing with respect to the inputs. The output is changing and the input is changing. Those details have been viewed in the waveform viewer. So it allows adding inputs, outputs, internal signals. So if we have the larger design, so the internal signals which are defined can also be viewed using the waveform viewer. It's not only input and outputs, you can add some of the other internal signals for viewing as well. So this allows this input, outputs, and internal signals to be viewed for the changes and over the simulation time throughout. And it offers that you can run it and pass for a while wherever need to be passed, and time step simulation controls are available. So what is the time step? We can specify that, and the simulation can be done with the time steps as well. So it supports the cursor for precise time measurement, in the sense, so we can place the cursor and then measure that time, so time duration for which this signal is changed from this to this, 1 to 0, or what is the changes in that can be with the precursors. It supports the cursors also. If it says that enables zooming, panning for detailed analysis, so we can view a particular portion of the waveform viewer and see the signal, the details of the signal. Also, it allows radix change. Suppose you mentioned that in the $monitor or in the code and the test bench, you use this binary. Okay, so you want to see that value in hex, decimal, or in ASCII. There are formats in which that this can be viewed as well. So, it allows the radix changes of the viewing signals. Also, it is allowing the grouping of signals. So, we have the A, B, C, there are 3 bits available, and you want to group it and see the output. So, it can be grouped, reordering of the signal, order in which it is viewed. So, X first, Y then next, or Z, Z and the third. So, you can reorder them to view the signal as well. This is small facilities that is helpful to visualize in the analysis. Also the coloring you can be chosen. So, the waveform viewer has this properties or the which could be changed into for better analysis. Even the layouts, if you see that the particular layouts can be saved and reused, the waveform layouts. So, once the simulation is done, the waveform editor pops up, and that portion of this layout can be saved for after, or it can for reviewing after also. And it has this, the waveforms which are shown in the waveform editor can be exported like for future use, or it can be those as a data, so that VCD value change dump formats, so are available to dump the data in this VCD format. So, the inputs and outputs can be exported as well. So, the markers and comments can be added to highlight the events. So, it is possible for the highlighting also on the waveform editor. The comments can be added, markers can be added also. So, with this is about the waveform editor properties, and in the test bench we have looked into the how initial blocks are used, how these inputs and outputs and the input combinations generated, how the initial blocks used in the case of printing the outputs also. So, this is one form of there is one example, the piece of a snap that which is taken for the example. So, suppose it is not only a single bit. Suppose if it has a 0 1, that is 2 bit which has a value 3, suppose 1 1. So, the first bit 0 and second bit 1. So, which is having the value 1 1, that is 3. So, how this multi-bit vectors can be viewed in the form editor. So, if you see that this is the first bit, that is 0 and this is 1, okay, this first bit is changing here as well as changing here and changing here, and the second bit, that is 0 1, is changing over this point, and it is kept 1 for rest of the time. So, these two, the combination of 0 1 is viewed here. This is the 0 0, so this gives the 0, and here you can see this is giving 1. Okay, so the value because of the 0 1. Okay, so this, and the change, you can see the data change, kind of data change is can be viewed at this. This is 1, and here this is 1 0. Okay, so this is 1 and 0. So, you can see the data change at this point, and it is shown 2. Also, the here 1 1, it is 3. Okay, so 1 1, the 2 bit, which is 3. So, this can be 0 1 2 3 displaying, and this is. So, the multi-bit vectors, by expanding the each bit, can be viewed in the waveform editor. So, similarly, there is another example, that is I of 0 to 3, that is 4 bits. Okay, so this 4 bits 0 1 2 3 are shown here. So, the first bit, and then the second bit, third bit and fourth bit, this is combination of all the 4 bits. Okay, so for example, this is 1 0 1 0. Okay, so we have this as 10. So, the 10 is viewed as it is shown here as this radix, and so it's A, okay, instead of 10. So, that is why it is showing A. Okay, so the 4 bits are combined here. There is no change shown over here, but it is to just changing the radix also possible to show that it is changing the radix. So, Y is 1. So, at this point it is 1. So, this keep changing, this is only 1 bit change here. So, it is not any output of any of the program, just to show this multi-bit vectors, how to view them. Each bit needs to be viewed, and the combined bit also can be viewed like this. This first one and then this portion. You can see the nanoseconds. This can be expanded, and you can see the resolution in the small scales that represent the picoseconds here. So this is the snap which is showing the multi-bit expansion of the variable, which can be viewed in the waveform editor or waveform viewer. So also this one would like to give you to the A, which is 1010. So we can change this radix here, the possible radix. You can see the binary, hexadecimal, octal and ASCII, and then this can be unsigned decimal, signed magnitude, and those things can also be viewed here. When you combine these multi-bit vectors, there is a possibility to change this radixes. So you may be writing in the code that it's binary, but you want to view it in other radix. So that's possible to do that. So even in the previous example, you can see if it is in binary 00, 01, 10, 11, that in the decimal it was showing 0, 1, 2, 3 in the previous slide. Now this is 00, 01, 10 and 11. So this is about the waveform viewers, to how to view them. Single bit we have seen in the example, and multi-bit, how do we view this? So now coming to the simulation part. So how the simulation, and what a little bit about the simulation, how the simulation is carried out. Generally, if you have the Verilog module done and test benches done, so the simulator can be used to observe the outputs of the Verilog program, but once that syntax and other things are correct, so semantics are correct, then it goes for the simulator used to observe the outputs. And if the simulation operation begins with this time t equal to 0, that is simulation time of 0. So the simulator at time t equal to 0, that initializes all signals to default value x. If you see some if you don't specify the initial values, then that 0 0 0, if you don't specify a equal b equal to 0 0, then what happens, this it at t equal to 0, it makes it all unknown default values x x x x. And whenever you are assigning the changing the signal test inputs, there it starts assigning the values. So it is default x x, and all signals or variables which are declared explicitly are also initialized to that value at time t equal to 0. Also this at the time t equal to 0, it is initializing them. Then the each concurrent statement is looked into. So it prepares the event list which has all concurrent statements. So the concurrent statements like continuous assignments, assign statement, instance are the built-in gates which are instantiated, or the always block or the initial, all of them are listed, are prepared as a event list. So this each one has the one, at least it requires one software process in the simulator. It is called the one software process. So out of the event list, one particular module is selected for the execution. Also before this execution, the module instantiations will also added up, so that the process which is calculated here with the concurrent statement, if there is any instantiation, that process will increase. It depends on the complexity of the instantiation. So the one software process, or two processes, three processes, and so on. So each concurrent statement can take one process or two process or three process, depends on the instantiation. So if you have multiple instantiations, it would be looping behavior, then it takes much software processes. So the event list attempt, all the software processes are scheduled for execution, out of which only one is selected for that. And if the selected one is always block or initial block, then within the always block, all the statements should be executed. Those are procedural statements. So it starts executing sequentially. So if it is, unless until if there is a delay, and there is a delay element or the delay statement, this whole always block is continued for execution. If there is a delay statement, okay, so in the always block, if there is a delay statement, then the whole process is suspended. Okay, so it waits for till that delay time. Okay, so it continues. The procedural statements can also have this looping behavior, so it can go into that and update other values as well. So those things have been taken care, and then the process will be completed either, or if there is any time delay, then it is suspended. So the next in the event list, next process, the next module, next concurrent statement is selected, and the same way it is executed, and so on. So every concurrent statement deserves for some process, a software process. So that process is one by one, it is executed. So this is continuing for all the processes. Okay, so all of the processes, this would be continued, and then the simulation stops or the completes. So the completion of one cycle, no, that is called the simulation cycle. So it takes that and one process, and then if this is done, and take the another process, and then a third process, and so on. If all the processes are completed, then it is called as one simulation cycle. So one simulation cycle, or you can call this as like an iteration of that. So if that it may assign during this execution or the completing the processes in one simulation cycle, there may be changes in net values are the variables. Okay, so those are updated, and then and then event list is looked into. So after this simulation cycle, we have this event list have been scanned again. So which event has to be taken care in this after updation of the nets and variables. So this is how the simulation cycle and the scanning of event list is continued indefinitely to complete all the components or the simulation complete. So until all the event list processes have been completed. So if the list is empty, then the full simulation is completed. So it can have number of simulation cycle. Also it depends on the event list, it continues, the simulation cycle continues. So this simulation is completed. As of here now, we have not included this blocking and non-blocking statements in the simulation cycle or in the event list. Okay, so after introducing the blocking and non-blocking statements, we can discuss about how these blocking and non-blocking statements getting executed during the simulation. So right now the modules which we have seen, that concurrent statements, the concurrent statements are considered to have the one software process, and then this software process complication can arise due to the instantiation, or can be looping behaviors can inside the procedural statement or always block can have the simulation stopped, suspended, and then or it waits. If there is a delay the statement encountered, it gets suspended and go to the next one in the event list. So this is how the simulation process, to just an overview of the simulation, and we will take some examples with respect to the time and how these particular statements are executed, what would be the output of them. We can see them in the detailed examples. So the synthesis process. So in the synthesis, there was the test bench, and then I had this simulation, and then the synthesis. Very brief about the synthesis. This is like the code which you write should be synthesizable. So I mean, it should find the code, the synthesizer should find a suitable hardware element or logic gates or the resources of the hardware FPGA for your code. So if it is not, then the code must be, we have to rewrite this. So for example, where the problem will be serial control structures. So the if else statements. So if you have mutually exclusive conditions, then there is no problem in the synthesize. It is easy to find the logic structures for it. So if statement, and then else if, else. Okay, so if all the conditions should be specified in the code, so then the result is only a series of logic gates. So in this process, you can say that the mutually exclusive conditions. If there is mutually exclusive condition, the case statement is preferable. So it is going to be a series of logic gates, if else, if else, and so on. Suppose for example, this ternary operator. Ternary operator it has a logic expression, question mark, true expression, and the semicolon. colon, and then it has the false expression. So if logic expression is true, the true expression is assigned, the false expression is assigned. So in that mutually the exclusive conditions are specified. So that case it is synthesizable, that is synthesized to Mach structure. So any of the, suppose in case of if-else statement. So if-else statement, one else condition is missing, then it would infer a latch. So that inferring latch will be dealt in detail with the, in the case of when we do this synthesis process and synthesis of each code, and we will see how this particular code is converted into the equivalent synthesized code, synthesized block diagrams. So the latch inference should be avoided in the code. That means the, every case statement should have the proper all the combinations of cases for a particular input. Also the default case needs to be specified when we introduce this case statements. We'll see that now. So otherwise this latch will be formed. If else doesn't have else condition, the latch will be formed. So this latches, formation of latches should be avoided in the synthesis process. So the code must be synthesizable. Thank you.